guided practice goes along with the first 3 videos in the dynamics narrative representation section. Weight always points opposite normal force. Is that true or false? This is something that most people think is true, but it's not. It's false. So the rule is that weight, or Fg, always points down. This is a fact. The other fact is that normal force always points perpendicular to the contact surfaces. These 2 things must be true. Sometimes that means that Fn is opposite Fg, but not always, right? That happens if you have an object and you have Fn from the surface here and Fg is down. Yes, then they're opposite, but not always, because you could have somebody pushing, right, a crate this way. This Fn is not an opposite Fg. This one is, but it doesn't mean that all normal forces are perpendicular to Fg. And I'll show you some examples where there isn't any perpendicular opposite force to Fg. Okay, all forces are essentially field forces, or otherwise known as action at a distance forces. This is also false. Fn, normal force, tension force, and friction force are contact forces. You must have contact in order for them to be present. There are lots of forces that are field forces, Fg, for example, your electrostatic forces, and many others are action at a distance forces, right? But not all, right? Some are. Only moving objects can encounter frictional forces. That is also false because by definition, static friction force is the force that prevents sliding due to friction. So friction is present, but it's stopping something from moving. So velocity is going to be 0. There won't be any motion. Okay. A rightward moving truck skids to a stop from a high speed. So here's my truck, and it's moving with some speed, and it comes to a stop. In here, it's accelerating or slowing down some distance, d. We'll call that d stop. And you want to know what forces are acting on it. So when we draw all the forces acting on this object, you're going to say there is a normal force from the ground. There is your weight pulling down, your gravitational force, right? And then because your wheels are locked, you're going to have some friction force that's causing you to stop. We ignore air resistance unless you're told otherwise. There's no magnetism here, there's no springs involved, and there's no ropes, so there's no tension. Sand is often placed on an icy road because what does the sand do? Well, it doesn't change the normal force, it changes the coefficient of friction, and it increases, it makes it more rough. So that's how you figure out that one. Forces, when unbalanced, always cause objects to. So the key word here is unbalanced. So by definition, unbalanced means they're not the same. An unbalanced force means net force. And when there's a net force, there must be an acceleration. That is a fact. So that would be E. You don't even have to read the rest to know that. What is the mass of a 3-kilogram object on Earth and one on the moon? So here again, we're looking at the definition. The definition of mass is that it is independent of location. It's how much stuff something is composed of. Therefore, if it's 3 kilograms on the Earth, right, and kilograms are the units of mass, so it's 3 kilograms on Earth and on the moon. There's no difference in mass when you change location. The weight of a 3-kilogram object, I didn't leave enough room, so I'm going to come up here. To find weight, we have an equation. It's mass times little g. So we would do 3, and on Earth, little g is 9.8, right? This is kilograms, this is meters per second squared. So this is 27.4 newtons. So this is on Earth. On the moon, the acceleration due to gravity is a different value. It's 1/6 that of on the Earth. So 9.8 divided by 6 gives you about 1.7 or so. So this will be 3 times 1.7, and that comes out to be 1 newtons. So, so the weight ends up being a sixth. Now, how did I know that? Well, because I've been doing this for a long time. But really what you want to do is if you didn't know it and it wasn't in your notes from some other source, then you need to look it up. So Google it. That's how we find out facts we don't know. Okay. Inertia is a force that keeps stationary objects at rest and moving objects in motion at a constant velocity. Is this true or false? Well, the biggest problem here is this beginning part. Inertia is a force. We only have 4 mechanical forces: normal, tension, weight, and friction. So this is false because inertia is not a force. So it's not a force, so what is it? It is a property of matter that depends on how much mass something has. Okay, so so notice what we're doing is every time we answer a question, we're going back to the definitions. We're looking for definitional proof. So this one, you can't, my copy came out poorly, I apologize. This should say 4 kilograms at 1 meter per second. This is 10 kilograms, and it's moving this way, where velocity is 0. This is 5 kilograms, and this is 2 meters per second, and hopefully you have a better copy than I do. So it's asking, rank them in terms of their inertia. Again, inertia is dependent only on mass. So you want to define that clearly. Only on mass, not on velocity. So you could just ignore the velocities and just rank them in terms of the biggest mass down to the smallest mass, right? 10 is greater than 5 is greater than 4 is greater than 3. So that's pretty easy. You just have to know what inertia is. You can't answer that properly unless you know that. A ball is thrown vertically upwards after it's released and moving upwards to the peak, it slows down. So it's moving up and slowing down. So this is my motion diagram. I draw that first. And what we've learned is that when you have acceleration, there must be a net force or unbalanced forces acting on the ball. If net, and it has to point, right, pointing in the same direction as the acceleration. This is the essence of Newton's second law, right? So Newton's second law says that net force and acceleration are directly proportional. They point in the same direction. That means, right, a net force means that the bigger force points down, right? So this net force pointing down, a downward net force means that the bigger force points down. Okay, so that's, right, that's what we have here. We have an unbalanced force directed downward. An object moving at constant velocity must do what? Well, if it's constant velocity, therefore acceleration is 0. If acceleration is 0, net force must be 0. So that means, therefore, forces are balanced and the object is in equilibrium. So we can get rid of no net force, right? Because that means right? We said net force is 0. It's not going to stop because stopping implies acceleration. Doesn't say anything about whether there's gravity on it or not. It's experiencing a balance of forces. That's true. We already said that. Not have a force of friction. No rule about that. Not have any. Well, they could have forces, but they just have to be balanced. So that's what we have. D is the right answer. A car is moving to the right and slowing down, right? Decreasing speed. We're back to this again, right? Decreasing speed means velocity, acceleration are opposite. Which of the following statements correctly describes the forces acting on the car? So if we know acceleration is to the left, then we know net force is to the left. If net force is to the left, then the left force is greater than the right force, which is A. So this is my reasoning, so you can just use that. Oh, sorry. And lastly, the action-reaction force pairs always act upon two different objects, not the same object. Well, this is true. The rule is when you're using third law, right? Third law says there must be an interaction between two systems. If you're going to draw a force on an object, it's got to be external, right? All forces are due to external causes. So if you have an action-reaction force pair, so let's say you have one force here and one force here, well, by definition, these forces, right, have to be on two different objects. So here's one and here's the other. Here's A and here's B. And this is going to be B on A, and this is going to be the force of A on B.